All right, recorded is rolling. Welcome to New Week, New Topic. It is Monday, January 22nd. A bunch of you guys just turned in your simple harmonic motion and waves quiz before I hit record. So thank you for doing that. I'll get that in the grade books. Your guys' Doppler effect puzzles. That was the last thing we were doing back on Friday. Most of you guys turned that in. There's some of you guys wanted to go home and make sure you had the right answer. So if you did that,
I left something in my ass to just last night here.
All right, and then today's going to be a posters and demos day. All right, you guys see all these new posters hanging up around? We're just going to look at those. Had some other stuff lined up, but I haven't had time to get to that. So here we go. All right, so last couple weeks we've been talking about harmonic motion and then waves, and now we're going to move on to, well, electromagnetic spectrum and optics, which is more waves, just like just visual waves, right? So here's the full electromagnetic spectrum. Electromagnetism is a type of wave where we're talking about oscillating electric and magnetic fields. So here's a good visual. We got long wavelength to short wavelength, right? Humans have divided this into like 7 categories, right? And your eyes can only detect a tiny, tiny, tiny portion of this whole spectrum. So all the colors of the rainbow, well, the longest wavelengths that our eyes can perceive and interpret, 750 nanometers, call that red. And then the shortest we can interpret, 3 nanometers, let's call that violet. There's some animals that can see like a little bit into the infrared, a little bit to the ultraviolet, but we have human eyes and human brains, and that's about what we can see. Okay. So what about all these other categories? Well, right, so you hit red, and if you keep increasing the wavelength, then you get to infrared, and then microwaves. Microwaves are maybe a few centimeters long, and then radio waves is like meters and longer. Right? Going the other way, you hit violet, and then get into ultraviolet. So it's like shorter and shorter wavelength, higher frequency. Then X-rays and gamma rays, right? And maybe different parts of the spectrum have a little bit different properties, physical properties, but they all travel at the speed of light. You guys remember one of the formulas we've been working with the last couple of weeks is the wave formula, speed equals wavelength times frequency. You guys remember that? Speed equals wavelength times frequency, right? Wavelength could be crest to crest, for example, one wavelength, right? Frequency is some number of hertz, right? All right, so all these categories of waves, they all travel at the speed of light. This is just a special speed. C is, you can call it 3 times 10 to the 8 meters per second. I'll call it 300 million meters per second. And every single one of these wave categories travels at the same speed. The speed of light is really the speed of all electromagnetic waves. It's really the speed of anything that's massless. Anything that doesn't have mass has to move at that speed. Right? Has some interesting implications. We'll talk about when we get to relativity. Right? But what that means then is that the longer the wavelength, the lower the frequency. So there's an inverse relationship between these two, right? So long wavelength is the low frequency, short wavelength, high frequency. So, right? Right. How about different physical properties possibly between these different categories? So, give you guys an example. Visible light. What materials could that go through or not? Right? Like these walls and the ceiling, visible light can't go through. We can't see the classrooms around us. Now that window right there, the glass window, visible light can go through. But you know what can't go through that glass window? Is infrared and ultraviolet. Okay. Glass will block that. Like, guys, if it's a really sunny day outside, do you have to wear sunscreen to protect you from ultraviolet? If you're going to be out, let's say at the beach for 3 hours or something, yeah, you want to wear some sunscreen, protect you from UV. Right? What if it's cloudy? Do you still have to wear sunscreen? Yep, the UV can go right through those clouds, right? Visible light, not so much. But what if you're going on a long road trip, like from here to California, and you're going to drive all day? Do you have to wear sunscreen in the car? No, because that glass blocks the UV light, something like that. Right? Another interesting property of EM waves is that they are transverse waves, exactly like my model up here showing that this is the classic transverse wave, right? The S-looking shape, right? And experiment you can do to show that is these polarizing filters. Now, these polarizing filters only let light through in one direction. Let's call it vertical and vertical, for example, right? Which is maybe how you want to. If you guys have polarized sunglasses, I bet it polarizes the light pretty well vertically, which is what you want because let's say you're driving west into the sunset and you got like a blinding light and you've got the horizontal road and the horizon, you got all this horizontal light, that's way too much light. So you want to allow sunlight through so you can see, but not all the excess. So you want to have it oriented vertical and vertical. It's like polarizing sunglasses, right? So if I pass these on top of each other, okay, vertical. I mean, most lights get through, it looks like. But what if I take one of these and turn it 90 degrees. Now I got vertical versus horizontal. Oh, look at that. Light's not getting through. You see it blocks it? All you have to do is rotate this. Light gets through, no light gets through. Ooh, that right there is evidence that light is specifically a transverse wave, because this wouldn't work if it was longitudinal or like a pressure wave. That wouldn't happen. But transverse, yeah, let's set through one direction. Okay. Hey, do you guys think you've ever worn? I bet you guys have. Have you guys ever worn any glasses where that specifically do have it oriented this way, like vertical and horizontal, left eye, right eye? What would that be for? Why would you? Huh? Why would you want glasses that had different polarization to each eye? Why would you want different kinds of information to enter each eye? What would that be good for? Guys ever watch a 3D movie? 3D, right? Right? That's one way to do it. Right? Actually, it's a little bit more complicated, some kind of like spiral polarization, but that's the basic premise, right? They used to way back in the day have red and blue, but let different information in each eye. All right, so there you go. So let's kind of kickstart us off to EM spectrum and optics. Right? Ooh, let's do a little bit of color theory. So there's two main categories of color mixing: additive and subtractive. And what's the difference here? So start with additive. This is what Isaac Newton figured out in the day. You guys ever taken a prism and shine light through it, like white light? He noticed that the light would break apart into colors. So you guys have probably seen like the album cover Dark Side of the Moon. They've got the prism refracting that light, and it color refracts different wavelengths refract differently. Right? The color spreads out, right? And then if you take all the colors and put them back together, you get white light, right? So how about oh, and I'm gonna show you guys too. So let me flip my screen over because I know it's a animation version, but let's see the actual photograph version of this. There we go. Right. So here's a red lamp, a green lamp, and a blue lamp shining at a wall. Right. And oh, look, this sort of Venn diagram. Look where they all come together. Hey, we got white light from 3 different colored lamps. Okay. What if I turn the blue lamp off and you just had the green and the red going? Where you have green and red, what color does that make? Yellow. Look at that. Right. If you look at a computer screen, your laptop screen, or your phone screen, let's say you get down like microscopic, there's really only 3 colors on any screen. Guess what those 3 colors are? Red, green, and blue, right? It's called the RGB standard, red, green, blue. That's it. Your phone screen only has 3 colors on it, red, green, blue. That's it, right? How do you get yellow? Oh, just the red and the green lights light up, right? How do you get white? Like, any white background? Now all 3 colors light up, right? How do you get black? They're not lit up at all, right? You just turned off, right? If you're reading black text, that's where no pixels are lighted up at all. So you guys got that, right? Right. Let's flip back over here. Okay. But maybe break out some paints. You want to make a painting, and you start painting something, and then you mix all the colors together. Oh, that doesn't make white. That makes like a muddy brown looking color, right? Right. Okay. Well, now you're thinking about maybe something like subtractive, right? This is like paint, printer, ink, right? Guys, what are the 3 colors in your printer ink? Yeah, these 3 right here, right? Yeah. Yellow, cyan, magenta, right? So this is a subtractive color mixing. This is like if you have yellow pigment or yellow paint, yellow ink, what that means is it'll take white light and it'll absorb everything except for the yellow, and it'll let that reflect back out into the world. Same thing for like cyan and magenta, right? How do you get green then, right? Okay, well, you can mix yellow and blue. You probably know that since like kindergarten, right? But what that means from a physics point of view is that this yellow pigment is absorbing everything the yellow mixed with the cyan, absorbing everything except for the cyan, right? And then collectively they're absorbing even more, and only the green wavelengths are able to escape back out in the world. Now, if you take that green and mix it with magenta, okay, well, now it's over. Now that absorbs everything, and now you're to black, right? So if your printer runs out of black ink, but you have color, you can still print black. It's just using all your color ink, okay? Here's color mixing. Ooh, this one's fun. Retinal fatigue. All right, so let me zoom in a bit more on this one. Get rid of that white border. There you go. All right. So guys, stare right at that center apple, and I'll tell you what's going on, what's this about. All right, so everybody's staring right at the center, right? Well, I'll tell you what's going on. See a really cool optical illusion here. Okay, so in your eyes, you have 3 different color detecting cones, one for red, one for green, and one for blue, right? And then your brain is able to put it all together and create all the colors, right? Of course, there's no such thing as like red electrons or anything, right? It's just like whatever electron configuration is reflecting that particular wavelength in the world, right? Right, but now your cones are getting used to what's already there. You know, kind of like you walk into a bakery, it smells like bread, but you hang out an hour, you don't really notice anymore because you become acclimated to that environment. And your brain is looking for changes, looking for differences. Right, right. So your brain is getting used to the colors right there. The cones are getting used to the colors that are there. Right, and when I remove this, it's going. You guys are going to see the opposite colors. Right, now one of those apples is a red apple. One of those apples is a yellow apple. And one is a green apple. I want you guys to tell me, see if you guys see this, left to right, which apple is which. All right, you guys ready to go? All right, ready? And pow. What do you guys see left to right? Yeah, I see green, red, and yellow. That's what I see from left to right. Green, red, and yellow apples. Right? And then that leaf is like a dark green color. Here, we'll do this one more time. All right, in case it didn't work the first time. Try this again. All right. So just keep staring at that middle one for a bit. Okay. Oh, and if you want to do this yourself, I can tell you how to do this. Give you guys a pointer. One thing, if you want to do this, like make your own picture, is use something that has just a few simple colors. You know, maybe like 3 or 4 colors. Flags work pretty good. I've seen flags done with this trick. But if you use an actual photograph, that's way too complex and there's like way too great. So actual photographs don't really work. You just want something more kind of cartoony with just like 3 or 4 colors. Okay. And then whatever picture you want to do, you guys know the program Paint, maybe on a computer, that you can use to invert the colors. I think it's like Control-Shift-I. I think we'll invert the colors. That's what I did here. Just did Paint. Right. So let's try this again. And oh, right. I see 3 regular colored apples. Right? Maybe not. For some guys. All right. So it's called retinal fatigue. All right. Work for some, not for all. Oh, here's another one that maybe might work for some, but not all. We got Newton's wheel and Venom's wheel. Sometime next couple weeks, I'll have you guys do this activity. I'll have you guys cut this out and put this together and spin this. Right. So actually, I do have a Newton's wheel right in front of me. I will flash this in front of the camera. Newton's wheel. Right. What did Newton say? If you put all the colors together, you get what color? White. Let's see. Right. Now this should work in class. Now I don't know in the video because the video is gonna have a frame rate. Okay. But you guys see it? It looks like white, doesn't it? Look at that. Right. Oh, there's all the colors again. No, there's white. I see white. Right. Now I'm curious to check this out on the video later. I don't know because the fact that the video has a certain frame rate, this might not work as well. But in class, it definitely looks like white. Right. Now, oh, there's all the colors back. Look at that. Oh, now Venom's wheel is clearly just black and white. There's no colors on the Venom's wheel. So what's that about? Oh, so give that a spin. And yeah, this is one that works for some people, but not everybody. When I spin this Venom's wheel, I can tell you what I see. I see like some like dark green bands, some dark red bands, some dark purple bands, like a sort of a dark gold band. Right? So this is getting at the idea that colors don't really exist in the sense that like there's no like yellow colored electrons or anything like that. There's no such thing, right? But there's different electron configurations that could absorb or reflect certain wavelengths back into the world, right? And then when you get these bands spinning, it creates that illusory effect in your eyes and in your brain, right? So yeah, we'll try that out here next couple weeks, right? Ooh, at some point I'm gonna have you guys make a zoetrope animation. So yeah, we'll eventually do that. So that'll be a fun activity one of these days. Coming up pretty soon. All right, let's talk about luminous flux, luminous intensity, illuminance. Right. So big picture, like how do you measure anything, or what units are we talking about here? Do you guys remember way back in August, I told you guys there's like 7 fundamental base SI units you can use to measure anything that we know how to measure. And the entire first semester, we only touched 3 of them. You guys remember mass was in kilograms, length was in meters, and time was in seconds. You guys remember that? Great. Those are the only 3 units we ever touched first semester. Now we combine those to make more complex units, like force measured in newtons, but that just broke down into some version of kilograms, meters, and seconds, right? Okay. But what if you want to say like how bright is something? Okay. Well, now we're gonna have to bring in some version of candelas, right? Now, and this is related to like human senses, like. Okay, so kind of an iffy one, right? We're trying to like objectively describe the world, right? So candela is one of these 7 base SI units. The other ones here, I'll just mention them real fast. There's like moles, but that's just counting things. You guys learned that one in chemistry, like moles. There's just a big number, right? Kelvin for temperature measured in Kelvin. and electric current is measured in amps or amperes, right? Those are the other ones. All right, but we're looking at like candelas here. Or another perspective could be lumens. Actually, I'm going to start with lumens, right? If you guys ever buy a flashlight from the store or like a bike light from the store, it might tell you how many lumens or candelas it is, right? And sometimes seen it even like one has like 4 lumens or candelas, and then you look another brand has more candelas than lumens. What the heck is going on here, right? All right, so here's a story. I'm gonna explain as best I can, but really, if you want to understand, I think it's a good idea to like go back and think more deeply on this, right? And these are just 3 measurements of like how bright is something. There's a whole list of other measurements too, but these are kind of the 3 main ones, right? So suppose you light a candle, right? So it's a dark room, you're gonna light that candle, right? And there's some total amount of light that's radiated into the room. We're gonna call that luminous flux, and we're gonna measure that in lumens, right? Okay. Then, what if you do this though? What if you take a mirror and you put a mirror right next to this candle flame, right? Well, on the front side of the mirror, now it looks like there's 2 candles, so now it's like twice as bright. But behind the mirror, well, all the light is blocked, so now it's completely dark. So it's kind of like all the light's been sent to one half, right? One half of the room, right? And now I'm getting towards the idea of this luminous intensity, which is going to be measured in candelas. What's that about? This is luminous flux per unit solid angle, right? So by putting a mirror here, the luminous flux doesn't change, right? The candle's still emitting the same amount of light as whatever it is, right? But the fact that it appears to be twice as bright on one side, you could say it went from like 1 candela to 2 candelas. So it doubled the luminous intensity, right? Is what's going on, right? Right. Now, there's another unit here that we haven't talked about yet called steradian, and it's going to measure a solid angle, right? The idea here is, suppose you put like a sphere, like a spherical shell around this candle flame. Can you guys imagine that spherical shell, right? Now, who remembers what is the surface area on a sphere relative to its radius? Surface area equals what? Is it 4 pi r squared, right? Is that right? 4 pi r squared, right? So suppose you have a sphere that's 1 meter radius, right? 1 meter radius, you guys got that, right? And I'm going to rope off 1 square meter. That area relative to that size sphere is occupying 1 steradian of a solid angle, right? Which isn't really something you can measure with a protractor. It's kind of like an angle, but you have to think in 3 dimensions, right? Right. And there's like some amount of light that would fall on that particular square meter, right? For a 1 meter radius sphere, right? So remember that sphere has a radius at that point of 4 pi square meters. So I'm focused on 1 square meter, right? And if there's 4 pi lumens of flux total, 4 pi lumens of flux, that's a really nice number to work with. What I can say is that there's 1 lumen landing on that 1 square meter. And then if you just expand that wedge out, that'd be a continuous ratio, right? How many lumens per steradian, right? And I can call that 1 candela, okay? So 1 candela sort of aligns with like 4 pi lumens of flux, right? They kind of go hand in hand, right? As long as there's like no mirrors involved. I did put a mirror here to maybe represent a flashlight, right? Isn't that true? If you have like a flashlight or bike light, they have like a curved mirror here, so they can sort of like direct a beam of light one direction, right? So that won't increase the flux, but it will increase the luminous intensity, right, in one particular direction, right? That's what flashlights go for. All right, finally, this last guy here, illuminance. What if you think, well, I know if I get further and further away from the light source, it looks dimmer and dimmer. Like, don't look at the sun, it'll burn your eyes out. But you can look at distant stars, right? That might have maybe a similar amount of flux, or maybe even more flux than our sun, but they're so far away. Oh, okay, okay. So how bright it appears to your eye, or maybe you could say like how much light is going to land on one of these square sections, right? That's why I put some squares in the back. Well, that's going to be proportional to 1 over the distance squared, right? Which is a lot like a universal gravitation. You guys remember universal gravitation? Gravity fields taper off 1 over the distance squared, right? To get further away from, say, a planet or something like that, right? Now this one I made a second poster for, right? So these two really go hand in hand, right? So I gave you guys an example. So we just got a candle flame and shows this out here, right? Now if it's 1 meter away and 1 square meter, my picture I should say is not exactly to scale. If it was to scale, this would be a wider wedge, right? But that aside, I think the idea across pretty good, right? Here's the same 3 concepts we're looking at: luminous flux measured in lumens, luminous intensity in candelas, and illuminance and lumen per square meter. That's also called lux. Got to see a couple of textbook questions where you might see that, right? So if you're 1 meter away, 2 meter away, 3 meter away, what would that be? Right? So suppose this candle flame is putting out 4 pi lumens of luminous flux, right? That's like how bright the candle is altogether, setting in all different directions, right? Like a sphere all around it, right? Well, that would mean that the luminous intensity is 1 candela, because 1 lumen would be landing on 1 square meter, so it's called 1 candela. And even if you back up further and further away, that ratio is still true, right? But luminance, right? Like how much light lands on, say, like 1 square meter, right? As you get further away. Okay, well now that's going to taper off 1 over the distance squared. It's about 1 lux, 1/4 lux, 1/9 lux, right? I guess that like that. Right. All right. So you guys see some textbook puzzles related to that. So you can measure something about how bright something is, right? Now this could have an application in astronomy, right? So look up in the sky. You want to quantify like how bright is that star, right? Hey, is that star brighter than it was last night? Is that star about to explode? What's going on there, right? Or maybe how bright is the star has something to do with how far away it is, or what temperature it is, or how big it is, or how far away a galaxy is, right? All these questions could go hand in hand, right? So what's the connection here? So start with say apparent brightness could be luminosity divided by 4 pi distance squared, right? Now luminosity, I haven't even mentioned yet. Notice this is in watts. If you think about it, you might say, oh, no. We were working with watts last semester. That has nothing to do with candelas or lumens or anything like that, right? That's just some combination of kilograms, meters, and seconds is what watts is, right? You might remember, I think I threw you guys a question that had to do with solar energy, like how large a field would you need to cover it in solar panels to meet some energy demand? Do you guys kind of remember a question like that, maybe? Right? I think it threw you guys a dimensional analysis question, right? So there's like some luminosity of sunlight that lands on Earth's surface, and if you were at Mars, you'd be further away from the sun, so that would be less, right? Something like that, right? And then, oh, actually, you see this connection here, right? Divide by 4 pi d squared. You guys know where the 4 pi comes from? That comes from the fact that, I point out from this last poster, the surface area of a sphere is 4 pi r squared, because that's the 4 pi connection, right? And then, so you guys see that connection right there, right? And then, okay, so some distance squared away. So let's say you're just round a star with a spherical shell, and then you expanded that spherical shell bigger, bigger, bigger until it finally reached Earth, right? Okay, that could be like the distance to Earth, something like that, right? Right. Now the connection back to, say like lumens or candelas is this connection right here, right? That there's, for green light, and I'm talking about like a specific wavelength, it's like 555 nanometers, I think, right? There's considered to be 683 lumens per watt, right? And this has to do with how bright you perceive that light to be in your eyes, right? Our eyes are most sensitive to green light. Our sun actually puts out more green light than any other color. We don't see the sun as green though. We see it as kind of a white yellow kind of color, but more green light. In the this luminous efficacy is most intense in right at that wavelength, 555 nanometers, which is like green light, something like that. Right. Okay, so that's a connection back to lumens and candelas then. Right. Here's a good formula: luminosity 4 pi times the radius of the star squared times the temperature to the power 4, and that's temperature, absolute temperature measured in Kelvin. Right, and then all connected by, multiplied by this called Stefan-Boltzmann constant right here. Right? So there you go. If you're ever doing astronomy, that you would run into those formulas. Right? So see some star in the distance, depending on how bright it appears to be, has some connection to do with its temperature, its size, and how far away it is. Right? It's all connected in there. Right? Ooh, spectral lines. So suppose we're in a laboratory and we're running white light through different elements. I have the first 8 elements here, right? Element 1, 2, 3, 4, 5, 6, 7, 8. Right? But you could do the entire periodic table like this, right? Well, each one of these elements will absorb and reflect certain wavelengths of light back into the world, right? Like hydrogen, I know it's kind of hard to tell in this projection, but I think hydrogen only absorbs a little bit. It's like there's a little band right there and there's a little band right here, and then everything else gets through, right? Helium, I see it like a band here and here, right? By the time you get to nitrogen, oh man, I see like bands all over the place, right? Okay, so what's this good for? Well, if you point a spectroscope, right, that's the tool you'd use, spectroscope, up at, say, like stars in the distance, then you can get a reading of, say, like what those stars are composed of, right? The more hydrogen, maybe the younger the star, and if it's been around for a few billion years, maybe it's fused a lot of hydrogen into helium, right? So I get an indication of that, right? Also, you guys ever read a headline says something like astronomers discover a distant planet that has water on it? Like, how would they even know? Like, we don't even have pictures of exoplanets, so how would they possibly know that there's one that's potentially Earth-like and has water on it, right? Well, what they do is they have these telescopes pointed at these stars, all day, every day. And then if there happens to be a planet orbiting a star and it happens to have its orbital plane that's aligned with Earth, which would be lucky, right? Then it'll pass in front of the star and we'll see the light dip a little bit, right? Then we can say, okay, well, there's a planet there. You get kind of an idea, do some math, figure out sort of how big is the planet, how far away is it from the star. We can get a pretty good idea mathematically, right? And then take out the spectroscope, and some of the star's light will pass through the atmosphere of the planet if it has an atmosphere. And if you get spectral lines that correspond to, say, like hydrogen and oxygen, oh, H2O, hey, there's atmosphere that has some water vapor in it. So that's that's how astronomers can know that a distant planet might have water vapor. Okay. Doppler effect. Oh, hey, that's what we were doing back on Friday. Doppler effect. Car goes by, you hear a pitch shift, but this is for light, right? So, hey, light's a kind of wave. I remember sound was a longitudinal wave, light's a transverse wave, but you can still get this Doppler shift. We get an observed frequency or an observed wavelength that's different than the source frequency or the source wavelength, right? That's what that would be, right? C is the speed of light. Give you guys that number here, 3 sig figs, right? About 100 years ago, a guy named Edwin Hubble was looking around at distant galaxies and realized that, here, say you go back to these spectral lines, for example, all these spectral lines were shifted a little bit to the right. Well, most of them were, right? Were shifted a bit to the right. So they were all sort of like red shifted. In fact, the further away the galaxy appeared to be, the more the red shifting was. And he put it all together as, oh, that means that the universe is in fact expanding. That's the evidence he was seeing through his telescope with this red shifting. The universe is expanding. Here's the math behind this, but we'll solve some of these in your textbook too. Okay. Yeah, and ever since then, we've known the universe is expanding. To do the calculations around the clock backwards, it's about 14 billion years ago. It looks like everything was kind of crunched together, same place, same time. This was like the first evidence for the Big Bang Theory. This is sort of where it comes from, right? Now, there is one galaxy that's blue shifted relative to us, and that's Andromeda Galaxy. So I forget, some billions of years from now, the Andromeda and Milky Way galaxy are going to collide. Red shift, blue shift. Okay. All right, let's look at, we're gonna look at reflection, and then we're gonna look at refraction, right? So having to do with light change of direction. Say you have a reflective surface, a mirror. This could be a mirror, right? Here's a candle sending out light in all different directions. I'm gonna follow one particular beam of light. What's it going to do when it hits this mirrored surface? Boing, it's going to bounce off about that direction, right? Now, how do you know exactly which direction? You're just following this one ray of light. So I'm going to draw a normal line. Now, normal, guys, what does normal mean again? Means, what's a synonym for normal? Perpendicular, right? You guys remember that? Right? Perpendicular to this surface, right? Whatever this angle of incidence is, the angle of reflection is just going to match that. That's it. That's the law of reflection. It's that straightforward. Now, this can get kind of fun if you have like a funhouse mirror. What if the mirror is not flat, right? What if it's like a funhouse mirror? Actually, get a little ahead of myself. Let me switch my screen over and play a Paul Hewitt demo for you guys. We're eventually going to do some ray diagrams with these, but just want to introduce this idea to you today, and then find the ray diagrams. We'll do those another day. Paul Hewitt. I'm so sorry, guys. Okay, here. So my screen's frozen, but what he's going to do is he's going to show that each of those reflects off according to the law of reflection, just like I showed you, right? So he's got 5 rays going. And then if you extrapolate backwards, see, like the candle flame is on the side of the mirrored surface, right? They'd be the side of the observer, right? If you extrapolate backwards into the mirror, you can show that there's going to be an image of a candle exactly on the opposite side. So when, say, you're brushing your teeth in the morning, you're looking in the mirror, you see an image of yourself that's the same size and on exactly the opposite side. So if you're standing 1 meter away from the mirror, your reflection appears to be also 1 meter away from that surface. I've been having trouble with this screen projection. It's been kind of doing that a little bit today. Right, so yeah, you have to sort of imagine the rest of that video right there. Right. So what if we don't have a flat surface? What if it's like a curved surface? And I want to start with a mirrored sphere. I'm going to turn this into a poster too. I just yeah, realized this would be a good poster. Yeah, thank you. Right, so so you guys see this is a giant mirrored sphere, right? It's a giant sphere with a mirrored surface, right? And maybe there's in the world all different images and in all different rays of light. I'm going to follow this one ray of light. Here comes a ray of light, maybe like a laser beam, right? It's going to hit the surface, and then law of reflection is going to bounce off going kind of that direction, right? Now, how can I quantify exactly what direction? Well, here's a normal line. So normal to the surface, perpendicular to the surface, it goes straight to the center of the sphere, right? Kind of makes sense, right? Okay. So this angle of incidence has to match this angle of reflection. It's going to be, right? Now, if you extrapolate backwards this ray of light, right, like the observer would say, oh, looks like it came kind of from back here, right? It's going to go always through, I could pick any ray, like going in any direction, and this reflected ray is always going to go through this focal point. You guys see focal point I have labeled right here, right? And it turns out that this focal distance from the surface is always half of this distance to the center, which is the radius. You guys see F is half of R. You guys see that? Right. So I wrote that right here. F is R/2. Right. Okay. So now we have a formulaic way to apply the law of reflection to curvy surfaces. Right. You guys see that? Right. So let's look at some of these ray diagrams. Again, I'm gonna have you guys do some of these next few days. Right. Here's the plane mirror. He was showing that sort of the candle, right? Here I have just a couple of rays going. So one ray going parallel to the ground, right? Now a flat mirror, guys, wouldn't a flat plane mirror kind of be like a sphere that's just infinitely big, right? Make a sphere bigger, 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 bigger. It looks flat, right? Right. And then you could say the center would be infinitely far away, so would the focal distance, right? So if you sort of apply this focal point process to this, right? Anyway, any light that hits a flat mirror straight on at 90 degrees, like aligned with the normal line, is just going to reflect right back, right? And then an observer would extrapolate and say, oh, it's like it came from that direction. Okay, so that's real straightforward. What about like a ray of light that's coming from a shoes, right? It's going to reflect, boing, maybe skirt off the top of his head right there, right? And then if you extrapolate backwards, looks like it came from back here, right? Now, that's just 2 rays of light. You could have like 10, 20, 100,000 rays of light, right? And eventually form an image. So 2 rays of light can tell you pretty much what's going on. Right? What if you look in the backside of a spoon? Right now we have a curvy mirror, right? And I labeled a focal point, which can tell you something about how curvy it is. Right? Do you guys see that the if this was a spherical surface, the center of the sphere would be just off the page right here, right? Because half of that distance, there's your focal distance right there, right? Okay. Because anytime you look in the backside of a spoon, which is what this guy's doing right here, so look in the backside of a spoon, you will always, always, always see a reflection of yourself that looks smaller than you are in the real world. Right? It looks like a short version of yourself, right? Right. Regardless of if you're really close or really far away. Right, so follow a couple of rays. This could bounce off, boing. Right, see it extrapolates backwards through the focal point. And what about a line headed straight for the focal point? That'll bounce off, boing, parallel to the ground. Okay. Where those 2 rays cross here, they cross here in the real world, they cross here in the reflection world, and got object image, boom, just like that. Okay. There's also a math formula you can use to determine where is the image going to be, right? Because you could use the ray diagram graphical method to figure out where is the image going to be, or you could use this math formula. So this says 1 over the focal distance is 1 over distance object plus 1 over distance image, right? Here it could be focal distance, here could be distance object, here could be distance image, right? The fact that these are on opposite sides of the mirror means you're going to have some positive and some negative numbers. So it might be a mix of positive and negative numbers here, right? We'll try that too. When we do ray diagrams, we'll break out this formula, we'll make equations and see how close the equations lined up with the picture. And they're usually pretty dang close. Right? But what if you turn the spoon around? So you have, say, a concave mirror. Right? Now, the image here, it depends how close or far away you're holding that concave mirror. If you hold it real close to your face, you'll see a blown up image of yourself, right? And that actually is what a cosmetic mirror is. So show that right here. Right here, I have two-sided. One side is a plain mirror, and the other side has a little bit of curvature to it. It's a little bit concave. So when you hold it close to your face, oh yeah, it'll blow up your image. So now you look really big. It's got a cosmetic mirror, right? We'll do the ray diagrams again the next few days, and you guys will all get to try it out. And maybe we'll break out that formula too, that algebra version, and see if it lines up, right? No, I'll call it upright. I'll call it a virtual image because it's on the opposite side. If you look at a plane mirror, it's also a virtual image. Like these two are also virtual images, right? But if you take that spoon or that cosmetic mirror and you back it up far enough away, something weird happens is that you actually invert upside down, right? So I'll call this an inverted image. And if you look real close, it might even look like the image is sort of hovering in front of the spoon in the cosmetic mirror. Okay, so I'll call that a real image, real as opposed to virtual. So it looks like this. And I have a demo of this too. So you guys have probably seen this, right? Right, you guys have probably seen this. So here I got takes apart. It's a couple of parabolic mirrors, both concave mirrors, right? Got a little plastic pig down here. Right, throw on the lid, and if I turn this in the right direction, it's going to look like there's. That's hard to get this guy right. Okay. It's going to look like there's a pig sort of floating like right above it. It's hard to get it exactly right here. Try one more time here. Right. I do have a video demo of this too, but my screen's not screen share not quite working right now. Right, so try to see if this is actually working on the. Okay, I think it's working on the video too. I think it's working on the video. Looks like there's a pig like right here. It's a really good illusion. So yeah, if you haven't had a chance to try this yet, go ahead. Right. If you want to do some extra experimentation, take these apart and hold it close to your face or hold it far away. You'll see at some point you're gonna flip upside down as you're holding it further away. Right, so it's a good one too. It's called a real image. Right, real image. Right. All right, now let's switch over because we've been looking at reflection. Let's switch over and look at refraction. I need to write that word on this poster too, refraction. Right, Snell's law of describing refraction. Right, you guys ever put a straw in a glass of water and it looks like the straw's bent? It's not really, right? Or your friend steps in a pool and it looks like they have really short legs. They don't really, right? It's just an illusion. Right, what's going on there? Right, so I'm going to do a more in-depth explanation of this a different day, but just for now, it's related to the fact that light slows down in different media, right? So this whole thing about the speed of light being 3 × 10⁸ meters per second, that's really only true in a vacuum. In air, it's almost true. It's like 99.9 something% true. So it's like, okay, we kind of round it, right? But in water, light does slow down significantly, and same in glass, right? And that kicks off this whole process that eventually causes it to bend. That, as a technical term, is called refraction, right? Right. So this N right here is called index of refraction, and it says what is the speed of light in a vacuum compared to speed of light, say, inside this material, right? For water, I know this number is like 1.33. Different kinds of glass have different values. One value might be like 1.5 for glass, right? Something like that, right? And you need that to be true to have refraction for, let's say, magnifying glasses to work. If you have prescription glasses, right, that all connects back to Snell's law, right? So I might have this ray of light, and then when it changes medium, say from the water to air, air to water, depending on which way you're going, it's going to refract. And I can take these angles, I can measure them with respect to, again, a normal line, right? This line is perpendicular to the surface exchange, like I said, right? So these angles, theta 1, theta 2. So index of refraction times sine of the angle is equal to the other index of refraction times sine of the other angle, right? And then you can make that connection there, right? So here comes this ray of light, it refracts, boom, up to this observer eyeball. This observer thinks that light came from back here, bing, right? It looks like the pencil is bent, even though it really isn't, okay? Right. There's sort of a limit to refraction, okay? Right. What if you have a fish way down here deep in the ocean? Right? Here's a fisherman trying to get him some fish. And okay, there's all different rays of light leaving this fish going all different directions. So I'm following 4 rays of light. Right? Now, one that goes straight up just keeps going straight up. That's not fair, right? One that goes kind of off in this direction. Okay, that's going to refract out maybe this way. Got different angles, right? It's some critical angle, it's called. The light's just going to refract at like 90 degrees to the surface, and then anything past that is just going to go into what's called total internal reflection, right? Where can't even break the surface anymore, right? So what does this fisherman see? Well, if this fisherman looks straight at the fish, he's not going to see him, right? Because all this refraction process. If he sees the fish at all, I can tell you where he's going to see the fish, right? So let's follow a ray of light that I didn't quite draw, but kind of runs nearby this one. What if there's a ray of light goes right up about here, and then refracts out this way and into his eyes, right? He would see that ray of light coming from this direction, and so he interprets the fish as being probably right about here. He says, oh, that fish is like just near the surface, and it's way off in the distance, but it's not. It's actually deep down in the ocean. Okay, there you go. Okay. Oh yeah, we'll do a lab with this. I have some laser lights and some prisms, so do this one day. Tells all lab. Check that out. Okay. Oh, lenses. Right. So we're back to ray diagrams, except the last set of ray diagrams we're looking at were for reflection, like mirrored surfaces, and this is for refraction. We're talking about, well, this first one could be a magnifying glass, right? Got a magnifying glass right here. Let's check this out. Right. Ooh, look, make stuff big. You guys see it? See it like making stuff big? That's that. Right. So, how's that? Oh, that's exactly what my ray diagram is showing too. Look, object image. Right. That's exactly that right there. It's a converging lens, right? So I'll do some ray diagrams for that one. Now, depending on how close or far away you hold this, you can get different outcomes too, right? If you have prescription glasses, you might have a converging lens, or you might have this one, a diverging lens. There's only sort of one outcome of the other ones, right? Only one thing here, right? I forget which one's for nearsighted, which one's for farsighted. I have to go check that. But if your glasses are thick in the middle, that'd be converging. If they're thick near the rims, it's diverging lens. And depending on your prescription, you might need one or the other. Right? Now you can take these lenses, put them together, and make some of the first telescopes, say like about 500 years ago, were these refracting lens telescopes. It got a converging, here I had converging, diverging, right? One of these Galileo used, one of these Kepler used, who used which model exactly, but refracting telescopes you can do some basic astronomy with, right? Now, one disadvantage of using refracting lenses for telescopes is that when you refract light, each wavelength of light refracts a little bit differently, and the colors spread out, right? It's called a chromatic aberration. So if you're pointing this type telescope at, say, Jupiter, you don't get a crisp image of Jupiter. You see kind of a fuzzy picture of Jupiter where the colors kind of spread out, right? Isaac Newton realized that and said, hey, we can replace one of these lenses with a mirror, right? And then you don't have any of that chromatic aberration. And all modern day serious telescopes are using Isaac Newton's model. So Hubble telescope is a reflecting telescope. The James Webb telescope just went up a couple years back. That's one of these two. Okay. Gives crisper images. Okay. Ooh, rainbow physics. So rainbow is a combination of both refraction and reflection. If you ever see a rainbow, I can tell you where the sun is. The sun is always behind you. Right? The rainbow you're looking at, well, there's a bunch of water droplets. Maybe it's like after a rainstorm, something like that. Right? So here comes the white light. It's going to first refract. Here's a couple of water droplets. You guys see water droplet, water droplet. I'm taking 2 water droplets. I'm going to show those, create a rainbow. Really, you need like billions of water droplets. But anyway, okay. So here comes a ray of white light. It's going to refract. Then it's going to reflect off the back. That's internal reflection. It's going to refract again. So the colors are spreading out. Right? In fact, they'll spread out at these angles exactly. Right? So here comes a ray of red light. That's at a 42-degree angle. Here comes violet. That's at 40 degrees. Now, if you were up in a helicopter looking straight down, you saw a rainbow, it would be a circle. Most of us, most of the time, we're down on the ground level, so we're really only seeing the top half of a circle, but it is a circular shape. That's what that is. It's always like 2 degrees wide, that rainbow right there. Okay. All right, what's some cool stuff we've seen with telescopes? We're looking deep out into space. Okay, we gotta make that's this last little time I have here. So you guys remember how we started today? We were starting with this electromagnetic spectrum. And I was showing you guys Doppler shift. So what if you had the more the universe expands, the more the wavelengths get spread out. It's like this red shifting. What if you had a telescope that could see, say, like in a microwave section and like crunch those wavelengths to make it visible? That's what this image is. This is like a baby picture image of the universe when the universe was, say, 380,000 years old. Before that, it was too condensed for light to exist, right? But right about that year, that's it. Yeah, a little bit more on that, but okay, rotate a little bit here. All right, so here's Hubble Deep Field. Did I tell you guys the story about the Hubble Deep Field? Hubble Deep Field? Okay, maybe I'll tell you guys the story one day. It's a good story, but there's a picture right there. Okay. Here's Einstein ring. I'll eventually tell you guys about gravitational lensing here in a few months when we get to relativity. So Einstein ring is a fun one. Here's a black hole picture was taken a few years back. So yeah. All right. That's about rings. So that's gonna be our pause point right there. Pause point right there.